All right, welcome back. So just right below last week, our law of combining volumes examples, we are going to start looking at molar volumes. So we're going to start with Avogadro's theory. Now, Avogadro is definitely a name that you heard before, which we're going to get into very soon. But he said that equals volume of gases at the same temperature and pressure contain equal number of molecules. So this, of course, leads right into the definition of a mole and what Avogadro is kind of known for with his number. So the mole is just the measurement of number of particles in one sample. So for gases, what Avogadro is thinking is that if you do have the exact same temperature, so they're moving at the same speed and they have the exact same pressure, therefore they're going to have the same volume and, of course, the same amount of molecules within that substance. So if you remember Avogadro's number, it is 6.02 times 10 to the power 23 atoms or molecules per mole. It depends on what we're dealing with. So remember, an atom is just a single unit of something. So like for if you have helium, 1 mole of helium, that's 6.02 times 10 to the power 23 atoms, because, well, helium is just one atom. But if you have a molecule like carbon dioxide, which is comprised of a number of different atoms, we have 1 mole of CO2 is 6.02 times 10 to the power 23 molecules, right? But we know that CO2 is made up of 3 atoms, right? So 1 carbon and 2 oxygen. So this whole idea of Avogadro's number, and of course the units here, we can use this as a conversion factor because we have atoms or molecules per mole. We can do this to actually kind of add up and count how many molecules or how many atoms are going to be in particular samples of gases. So when we look at our first example right here, the question states how many molecules are found in 56.9 moles of hydrogen gas, and how does this compare with the same number of moles of carbon dioxide? So from previously, we know that if they're under the same temperature and pressure, we should have the exact same number of molecules, but we are going to prove that mathematically. So we're going to compare hydrogen and carbon dioxide. So I'm just going to split them up like this. Now for our hydrogen, we're starting with 56.9 moles of hydrogen. Now we are going to use our conversion factor, which is going to be Avogadro's number. So we are trying to get rid of moles. So in Avogadro's number, we know for every 1 mole, there's 6.02 times 10 to the power of 23 molecules. So of course, if we use this, we'll notice that the units for moles will cancel out. The unit we're left with is molecules. And the answer we get, if you put this into your calculator, is 3.43 times 10 to the 25 molecules, of course, of hydrogen, H2 gas. Now we're going to do the exact same thing with carbon dioxide, and should be no surprise that we are going to get the exact same answer, just because this is kind of what Avogadro's number said. So we know, same thing, there's 6.02 times 10 to the 23 molecules in every 1 mole. So just like before, our unit of moles cancel out. We're left with units of molecules. I forgot to put in my equal sign up here, and that is equal to 3.43 times 10 to the 25 molecules. In this case, it's of CO2. Right here, just mathematically proving that, of course, if we do have the same number of moles of a particular thing, we're going to have the same number of molecules. Now, our second question here is a little more complex, is just because when we just kind of read ahead, it's after a long day's work, we have Manuel Hernandez was bored, so he decided to count all of the atoms of oxygen from using his superhuman sight. He counted 1.34 times 10 to the power 26 atoms of gas, and we need to figure out how many molecules and how many moles there are. So there's 2 different conversion factors we're going to need in order to answer this question. First of all, we have to figure out, well, how many atoms are going to be in 1 molecule of oxygen gas, and then of course how many moles are in that, or how many moles or how many molecules are in 1 mole. So our 2 conversion factors for oxygen, if you remember, oxygen is equal to O2. So we have 2 atoms for every 1 molecule and we know there's 6.02 times 10 to the 23 molecules in every 1 mole. So these are our two conversion factors that we need to use. So of course, I'm going to solve for the molecules first, and then next is going to be the moles. So if we know that there's 1.34 times 10 to the power of 26 atoms of oxygen he counted, so our conversion factor, there's 2 atoms for every 1 molecule. And we get an answer of 6.70 times 10 . All right, hold on one sec. 25 molecules. All right, and the reason for that, the atoms cancel out. So that's our answer for part 1. Oh, sorry, kind of scratched out. So that's how many molecules. Now as for how many moles, we go down for part 2, so 6.70 times 10 to the power of 25 molecules. We use our conversion factor again, so there is 6.02 times 10 to 23 molecules in every 1 mole. And of course we put that into our calculator and we get 112 moles. And of course with 3 significant digits, and with rounding. Oh, sorry, should be 111, not 112. Sorry, my bad. There we go, so 111 moles of oxygen. So that's kind of using this whole idea of conversion factors where we can actually count how many molecules, how many moles, how many atoms there are in any number of samples that were given. Now, this whole idea ties into what is known as the molar volume, because as Avogadro kind of stated, that if we have equal temperature and pressure, then every sample should have the exact same number of moles. So what the molar volume is the volume of 1 mole of gas, a substance, the volume 1 mole of a gas substance. There should not be an A there, sorry. Sorry, the word there isn't going to be substance, it's the volume 1 mole of gas has at a specific temperature and pressure. Sorry, the notes got a little messed up there. So molar volume is the volume 1 mole of gas has at a specific temperature and pressure. So the molar volume is going to be the same for all gases at the same temperature and pressure. So the 2 common conditions we're going to be dealing with is SATP, if you remember, means standard ambient temperature and pressure. And the units for this, so the molar volume at SATP is 24.8 liters per mole. So just pay attention to the units here. And of course, the other common condition is going to be STP. And this is 22.4 liters for every 1 mole. These values can be found on the back of your periodic table in the bottom right-hand corner, where it's going to read VSTP and VSATP. Now, just for our equation, these are going to be converted into Vm for molar volume, just because we can be talking about any of these standard conditions, so we can just put it in once we read the question, know which one we need to use. So our formula for volume calculation, we got N is equal to V over Vm. And then, of course, we can rearrange this because we looked at rearranging before. We can solve for Vm. We're going to just put up here, right? Vm is equal to V over N. And if we want to solve for V is equal to NVM. So that's those rearranged. Of course, we can use dimensional analysis as well. And volume must be in liters. So our first example that I have right here, what volume is occupied by 0.024 moles of carbon dioxide gas at SATP? So we know N is equal to 0.024 mole. We have two significant digits there. VSATP can be found above or back of periodic table, 24.8 liters per mole. V is equal to, we don't know. So we can either use dimensional analysis or equations. So our equation way, of course, once we have our variables, we have our rearranged equation. V is equal to NVM. So we can put this in. And we can get a volume of 0.60 liters. So that works. Or we can use dimensional analysis where we know our molar volume where it has two different units right now. We can use that as a conversion factor. So if you just start off with 0.024 moles, our conversion factor, well, we want to cancel out moles. So in every 1 mole, there's 24.8 liters. And this way right here, our unit for moles will cancel out. And we are left with 0.60 liters. All right, so it doesn't really matter which one you use to solve as long as you show your workings and you know which one's there. All right, so that was the first one. Now I want you to pause the video, try the second one, and the answer is going to go up in 3 seconds. All right, and we have our two answers up here. So one of them is done using the equation, so when the rearranged equations up above. Now, of course, you will need to know how to rearrange the equations. So if you're not sure, just go back and look at our first introduction to rearranged equations on Boyle's Law and Charles' Law. And then, of course, if you're still having trouble, I can help you out on a Google Hangout when we do that later on in the week. And, of course, our dimensional analysis will look something like that. All right, so of course, if you notice that where we do have molar volume in there, the moles come in. If you remember last time we seen moles, is we use molar mass in solving for massive things. So this is where we're leading with this right here as well, because where we're solving for number of moles, it's kind of that universal thing that every single chemistry equation will have number of moles in it. So if you remember, molar mass is the mass of 1 mole of a sample. The units is grams per mole, and the identity of the substance definitely matters. All right. So remember, when we're calculating, you write the correct chemical formula first. You determine the number of each type of atom that's present. And of course, if there's 2, we multiply by that number, and we multiply by the atomic mass we found in the periodic table, and then we add everything together. Now, we kind of went over this when we did our Science 10 review, but I'm just going to do a quick little reminder with the first few here. So calcium nitrate, tetrahydrate. So first thing is making sure that we actually have our correct chemical formula first. So remember, calcium nitrate, we have to look at your periodic table. Calcium ion is Ca2 plus, nitrate is NO3 1 minus. You're going to have to drop and swap, so the 2 drops from the calcium and goes in front of the nitrate. The 1 from the nitrate drops and swaps in front of the calcium. So you get Ca1 we never write, and then we have 2 nitrates. So because it is a polyatomic ion, we need to make sure we enclose it into the brackets. All right, so that's just the calcium nitrate portion right there. So you get CaNO3 2, and our tetrahydrate, remember we put those in there by having a little dot. Tetra is 4, hydrate means water. So that is the chemical formula for calcium nitrate tetrahydrate. Now what we have for all of our atoms, we can start counting. So we got 1 calcium. We have 2 nitrogens. We have 6 oxygens. So that's just from all that, but we can go back. I forgot to add in the oxygens from water, so I'm going to count that. So we have 6 oxygens from our calcium nitrate, and then we have another 4 coming from our water, so that's 10 oxygens, and then finally we have 8 hydrogens. So our 1 calcium, right, that's 1 times molar mass of calcium is 40.03 grams per mole. Our nitrogen, we got 2 times, it's 14.01 grams per mole. Our oxygen is 16.00 grams per mole, and our hydrogen is 1.01. So of course we simplify all this. Alright, so all those are simplified, and when we're done, we just add them all up together, and we get 236.18 grams per mole. And that is for our calcium nitrate tetrahydrate. Of course, we do have a bunch of other ones right here. So we got our iron 3 chloride, our bromine, our nickel 2 oxide, tetraphosphorus decaoxide, aluminum sulfide, and copper 2 sulfate pentahydrate. All right, so please pause the video right now, fill in all the chemical formulas and their molar masses, and I'll have all that up in about 3 seconds. All right, and here they are. So of course, just make sure to check all your workings, and of course the big thing is making sure you get the correct chemical formula first. So if you're still unsure with some of those, please review our first unit where we did go over all of this naming stuff and how to get the correct chemical formulas from the drop and swap and everything like that. So how this is going to be used is we have right here. So we're going to have 2-step calculations, or you can do 1 step if you do dimensional analysis. So this is where you are going to notice you're either given a mass or you're given a volume. It's going to be under STP or SATP conditions, and we solve for one of our unknowns. So I'm just going to go over example 1 with you, and of course same thing as before, I'll let you pause the video and then try the other ones, and I'll put the answers up. So our first one right here, what volume of gas would 6.89 grams of chlorine gas occupy at SATP? All right, now because we have mass is equal to 6.98 grams. Now normally whenever we have a mass, you should always get in the habit of writing down the molar mass, because if you have a mass, there's a good chance molar mass is going to be used as well. So for chlorine, remember it's a diatomic Cl2, so the molar mass is 70.90 grams per mole. What volume it's asking? At VSATP is equal to 24.8 liters per mole. Now, the starting point for these here is always just going to be, all right, what information do we have enough for? Because we know we're going to have to use 2 equations. We have our mass and molar mass equation. Actually, so number of moles equal to mass over molar mass, and number of moles equal to V over Vm. Now, obviously, with this question is asked for what volume, right? We're going to have to use this equation second, rearrange it, and of course solve it. So we are going to have to solve for number of moles first, right? So 1, find n. So number of moles is just equal to mass over molar mass. So we have our 6.98 grams divided by our 70.90 grams per mole, and we get number of moles is equal to, it's going to be a small number, which is fine, 0.098449 moles. Second, find volume. So we got volume is equal to NVM. So the number of moles, which we just calculated in our previous example, and our molar volume is 24.8 liters per mole, and we get our volume, in this case right here, 2.44 liters. And that is our answer. So it all comes down to you knowing that you're going to have to use 2 equations to do it. It's just a matter of looking at our 2 right here, figuring out what information we have, which one's enough to kind of solve for at least one thing, and then using that to solve for our next one. All right, so step 2, I want you guys to pause the video and try equations 2 and 3, and I'll put the answers up now in 3 seconds. And these are the answers completely worked out here. Now for example 2, if you didn't get this answer of 0.0724 grams, I just want you to pay close attention right here because our volume was in milliliters and our molar volume's in liters, so you need to convert this into liters before you can solve, right? So that's why we have 0.0600 liters there. And same thing with step 2, we notice our mass was in kilograms, but I need to convert that into grams because the molar mass equation is in grams. All right. Now you can use all these having dimensional analysis as well. So depending on if you tried it with dimensional analysis, oh, sorry, that completely went wrong there. So if you tried it using dimensional analysis and you're still getting those answers, awesome. If you're still not sure how to do it with dimensional analysis, just fire me off an email and I can send you the workings for those as well. All right, so that is that lesson done right there. So you guys can jump right ahead in your COE book. And of course, next lesson is going to be on the ideal gas law and the end of our gas unit. All right, awesome. See you guys later.